Hello everyone. Welcome back to my course Aerospace Engineering, Basics of Aerodynamics. In this video, we will talk about aerodynamic efficiency and performance metrics. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. Introduction to aerodynamic efficiency and performance metrics. Aerodynamic efficiency describes how effectively a body moving through air converts the energy of the flow into useful aerodynamic forces while minimizing losses. In practical terms, it answers a simple but fundamental question. How much useful force do you obtain compared to how much resistance the air creates? This concept is central to the design and performance of aircraft, automobiles, drones, wind turbines, and many other engineering systems that operate in air. A key physical quantity underlying all aerodynamic forces is the dynamic pressure, which represents the kinetic energy of the airflow per unit volume and is defined as dynamic pressure equals 1/2 multiplied by air density multiplied by the square of flow velocity, where ρ is the air density and v is the velocity of the flow. Aerodynamic forces acting on a body. When an object moves through air, it experiences several forces due to the interaction between its surface and the airflow. Lift acts perpendicular to the incoming airflow and is usually the force that allows aircraft to fly or vehicles to generate downforce. Drag acts in the opposite direction of motion and represents aerodynamic resistance. Thrust is the force provided by engines or propellers to overcome drag, while weight is the gravitational force acting downward. Aerodynamic efficiency mainly concerns the relationship between lift and drag, because lift is usually the useful force and drag is the primary loss. The fundamental expressions for lift and drag are lift equals 1/2 multiplied by air density multiplied by the square of flow velocity multiplied by reference area multiplied by lift coefficient. Drag equals 1/2 multiplied by air density multiplied by the square of flow velocity multiplied by reference area multiplied by drag coefficient, where S is the reference area, CL is the lift coefficient, and CD is the drag coefficient. These equations show that lift and drag depend on air density, flow speed, geometry, and the aerodynamic characteristics of the body. Meaning of aerodynamic efficiency. Aerodynamic efficiency is a measure of how well a system produces lift or thrust while minimizing drag. A highly efficient aerodynamic design produces the required lift with as little drag as possible. This efficiency directly affects fuel consumption, range, endurance, speed capability, and overall performance. The most common quantitative expression of aerodynamic efficiency is the lift-to-drag ratio, written as lift divided by drag. Using aerodynamic coefficients, the same ratio can be written as lift-to-drag ratio equals lift coefficient divided by drag coefficient. A higher lift-to-drag ratio means that the object can travel farther or use less energy for the same task. For example, a glider with a very high lift-to-drag ratio can travel a long horizontal distance while losing very little altitude. Lift-to-drag ratio and its physical interpretation. The lift-to-drag ratio is not constant. It changes with speed, angle of attack, and configuration. At low speeds, drag is dominated by the effects of lift generation, while at high speeds drag is dominated by friction and pressure effects. Somewhere between these extremes, there is a condition at which the lift-to-drag ratio is maximized. This point represents the most aerodynamically efficient operating condition. Mathematically, the condition for maximum aerodynamic efficiency can be expressed as derivative of lift-to-drag ratio with respect to angle of attack equals 0, where alpha is the angle of attack. In aircraft performance, the speed corresponding to maximum lift-to-drag ratio defines the best glide speed and the speed for maximum range. In automotive aerodynamics, although lift is often replaced by downforce, a similar concept applies. Designers aim to achieve the required downforce with the smallest possible drag penalty. Drag and its influence on efficiency. Drag is the main factor limiting aerodynamic efficiency. It represents the energy lost to the airflow due to motion through the air. Drag arises from several physical mechanisms. Parasite drag comes from the shape of the body and the friction between air and surface, and it increases rapidly with speed. Induced drag arises as a direct consequence of producing lift and is strongest at low speeds. At high speeds, especially near or above the speed of sound, wave drag appears due to shock waves. The total drag experienced by a body is the sum of these components, and their relative importance changes with speed. Aerodynamic efficiency improves when the total drag is minimized for the required lift. A commonly used drag model is the drag polar, written as drag coefficient equals 0 lift drag coefficient plus constant multiplied by the square of lift coefficient, where CD0 is the 0 lift drag coefficient and the second term represents induced drag. The total drag force then follows directly from the drag equation. Aerodynamic coefficients as performance metrics. To compare aerodynamic performance across different sizes, speeds, and environments, engineers use dimensionless coefficients. The lift coefficient represents how effectively a shape produces lift relative to dynamic pressure and reference area, while the drag coefficient represents how much aerodynamic resistance the shape produces under the same conditions. These coefficients allow performance data from wind tunnels or simulations to be applied to real vehicles. Because lift is proportional to the lift coefficient and drag is proportional to the drag coefficient. The ratio lift coefficient divided by drag coefficient becomes the primary metric for evaluating aerodynamic efficiency independent of scale. Optimal operating conditions and efficiency. For any given aerodynamic configuration, there exists a specific angle of attack and speed at which efficiency is maximized. This corresponds to the maximum lift-to-drag ratio. Operating at this condition minimizes the drag required to produce a given amount of lift. Another important condition is the speed at which total drag is minimized. At this speed, induced drag and parasite drag are equal in magnitude, which can be expressed as induced drag equals parasite drag. These operating points are critical in determining range, endurance, and fuel efficiency for aircraft and energy consumption for ground vehicles. Power requirements and aerodynamic performance. Aerodynamic performance can also be viewed from a power perspective. The power required to maintain steady motion is given by power equals drag multiplied by velocity. At low speeds, high induced drag requires significant power to maintain lift. At high speeds, parasite drag dominates and power requirements increase sharply. The resulting power curve has a minimum point, corresponding to minimum power required. For aircraft, maximum endurance occurs near the minimum power condition, while maximum range occurs near the maximum lift-to-drag condition. Aerodynamic efficiency improves when the power required for a given mission is minimized, which is why reducing drag is so important in performance-oriented designs. Reynolds number and its effect on efficiency. The Reynolds number is a dimensionless parameter that describes the relative importance of inertial forces to viscous forces in the airflow and is defined as Reynolds number equals air density multiplied by velocity multiplied by characteristic length divided by dynamic viscosity, where L is a characteristic length and mu is the dynamic viscosity of air. Reynolds number strongly influences boundary layer behavior, flow separation, and skin friction drag. At high Reynolds numbers, flows tend to be turbulent but more resistant to separation, while at low Reynolds numbers, flows may remain laminar but are more sensitive to disturbances and separation. Aerodynamic efficiency can change significantly with Reynolds number, which is why small-scale vehicles, such as drones, face different aerodynamic challenges compared to large aircraft. Mach number and compressibility effects. The Mach number represents the ratio of flow velocity to the speed of sound and is defined as Mach number equals velocity divided by speed of sound, where a is the speed of sound. At low Mach numbers, compressibility effects are negligible, and aerodynamic efficiency depends mainly on shape and viscous effects. As Mach number approaches unity, shock waves form and cause a rapid increase in drag, reducing aerodynamic efficiency. This phenomenon is often referred to as drag divergence. Geometric design and efficiency. The geometry of a body has a major influence on aerodynamic efficiency. Long, slender shapes and wings with high aspect ratios reduce induced drag, while smooth surfaces reduce skin friction. Features such as winglets, fairings, and carefully contoured profiles are used to control airflow and reduce losses. Induced drag, for example, can be approximated as induced drag coefficient equals square of lift coefficient divided by the product of P, Oswald efficiency factor, and wing aspect ratio, where AR is the aspect ratio and E is the Oswald efficiency factor. Every geometric choice involves trade-offs between efficiency, structural weight, stability, cost, and operational requirements. Practical trade-offs in aerodynamic design. In real engineering applications, aerodynamic efficiency is never the only objective. Designers must balance efficiency with structural strength, controllability, safety, manufacturing constraints, and cost. A glider prioritizes maximum lift-to-drag ratio above almost everything else, while a fighter aircraft sacrifices efficiency to gain maneuverability and high-speed performance. Road vehicles often accept higher drag to generate downforce for better handling and safety. Overall summary. Aerodynamic efficiency is fundamentally about achieving the required aerodynamic forces with the smallest possible losses. Performance metrics such as lift-to-drag ratio, lift coefficient, drag coefficient, power required, Reynolds number, Mach number, and optimal operating speeds provide engineers with the tools to quantify and improve this efficiency. Understanding how drag is generated, how efficiency varies with speed and flow conditions, and how geometry influences performance is essential for designing any system that moves through air efficiently. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. Which of the following best defines aerodynamic efficiency? The correct answer is the ability of a body to produce useful aerodynamic forces while minimizing drag. Question 2. The lift force on a body moving through air is directly proportional to which of the following? The correct answer is air density, velocity squared, reference area, and lift coefficient. Question 3. At the speed where total drag is minimized, which condition holds true? The correct answer is induced drag equals parasite drag. Question 4. What does the Reynolds number describe? The correct answer is the relative importance of inertial forces to viscous forces in the airflow. Question 5. Induced drag coefficient can be approximated by which of the following formulas? The correct answer is induced drag coefficient equals square of lift coefficient divided by the product of P, Oswald efficiency factor, and wing aspect ratio. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics, and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with Aerospace Engineering, Avionics, and Aerospace Systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the last unit and make a summary and review of what we have learned during this course. See you in the next video. Bye.